All right, so the first chapter just introduces you to encryption. So there's the basics of encryption, and we're going to talk about classical ciphers, the ones that were developed centuries ago, which are no longer in use alone or directly, but they do form the basis of modern encryption. Then we'll talk about the one perfect system, the one-time pad. This is what all systems are attempting to approximate. And then we'll talk about asymmetric encryption and how things can go wrong. So here's the basic idea. You have plain text, which is some kind of readable message, and you want to encrypt it with a key and turn it into ciphertext. And the idea is that this process should not be reversible. Only someone who has the key will be able to decrypt the ciphertext and see the plain text. And hopefully the key is long enough and the encryption algorithm is complicated enough that nobody can figure out how to recover the plain text without holding the key. That's what creates your confidentiality, is the main form of security you're looking for here. You would like to be able to publish this ciphertext in an insecure place like the internet and have some degree of confidence that nobody is going to be able to read the plaintext message inside except the authorized person who has the key. All right, so the classical ciphers. One of the oldest ones is the Caesar cipher, goes back more than 2,000 years. So you just take each letter and move it forward in the alphabet. So C, D, E, F, A, B, C, D, and so on. So moving each letter forward a few in the alphabet, the letters are scrambled. And in an era when very few people could read at all, this small shift was enough to be military-grade encryption at that time. Of course, these days, it's not very secure at all. Now, you can do this easily in Python, and you don't need to write Python scripts for this course, but it will help. And I do have quite a lot of demonstrations and projects where we use it, because it is the easiest way to demonstrate these things. Python is the easiest modern language to use, and I highly recommend practicing with it. Anyway, so here's the first Caesar script. So I put in the letters A through Z, then I input plain text and a number to shift it, and now I just create a ciphertext string, and for each letter in the plain text, I find the plain text letter, add the shift, and then add that letter to the ciphertext. So this will preform the Caesar cipher. Python 3 Caesar 1. So if I give it hello and a shift of 3, it turns it into K-H-O-O-R, H-I-J-K, and so on. Each letter just moves forward 3 spaces in the alphabet. Notice that the double L turns into a double O. Every single letter is encrypted separately, and if another letter appears again, it just turns into the same ciphertext. This, as we're going to see, is a weakness in the system, but that's how the Caesar cipher works. So you can break it with a simple brute force attack. All you have to do, there are only 26 possible shifts. So all you have to do is try all 26 shifts and just print out the result. So if you want to crack something, let me get a copy of this ciphertext core. If I do, Python 3 Caesar 2, it'll ask me for the ciphertext, and now it just tries every possible shift. And I can find the one that I can read, and therefore I can crack it without knowledge of the key. This is a fundamental problem. There are just not enough possible keys in the cipher, in the Caesar cipher, so it's easy enough to just try them all. There's another property that is not as obvious, which is that if you get the key wrong, you get meaningless garbage. That'll come up again later. That's an important feature. Only one of these is readable, so that means I can decrypt it without the key. For the one-time pad, as we're going to see, the problem is, even if you do a brute force attack, you create many readable answers and you don't know which one of them is the plain text. But in the Caesar cipher and most encryption schemes, that's not a problem. Now, the Vigneri cipher, which I'm probably pronouncing wrong, it's French, had another way you do it. You have a repeated keyword. So the keyword here would be not incredibly obvious. But anyway, you would take some keyword and repeat it over and over and use that to determine the Caesar cipher. And so here, I guess it's they drink the tea is the phrase you're going to use to encrypt the message with. And I guess the message is duh, duh, duh. Okay. No, I guess the message must be they drink the tea, and the keyword must be DUH, DUH, DUH. That's what he's doing. So all it means is you use a shift of 3 here, and a shift of 20 for here, and a shift of 7 here. So that's the pattern. And if you have a 3-letter word here, and this 3-letter word hits the same spot, then you'll get a repeat here. So it's the extension of the one I mentioned before, where repeated plain text turn into the same ciphertext. Here, there are groups of plain text that will eventually repeat and turn into groups of identical ciphertext. And so once again, that will let you crack it. And in general, this is the solution for many of these types of ciphers, is frequency analysis, because the letters are not all equally likely in English. E is by far the most likely letter, then T, then A, then O, then I. So if you just count the letters, even in something that's as short as a paragraph or so, it's very easy to tell which is the most common letter, and that's almost certainly E or T. So you can narrow down the guesses that way. And you can do that here if you make a longer ciphertext. So let me go to my demonstration here. Let's get the first sentence of the, zooming in didn't work. Oh, there we go. Let's get the first sentence of the Gettysburg Address here. So we got a longer piece of plain text to work with. And now, Caesar 2, I think? No. Must be Caesar 3. All right, so I give it the plain text, 7 years ago. And, how rude. All right, it worked before. It's probably got something to do with copying text from a web page and getting something like a stupid carriage return at the end or something. No, still invalid syntax. Well, I'll just go with I tried it before class and it worked, but somehow it's not going to work now. So I'll just use my slides. Some bad character is coming off the web page or something. Anyway, you can encrypt it to ciphertext like this, and then you can expose it to frequency analysis. So you can just count how often each of the letters appear, and you'll get a pattern like this, 18 H's and 15 W's and so on. So this is E, F, G, H. E is the most common letter, T is the next most common, U, V, W, and see, it follows the pattern. Even with this small sample size, the most common letter is the shift of E, the next most common letter is the shift of T, so you can easily figure out the shift is 3 and crack it that way. And this is the cryptanalysis, where you find some kind of flaw in the algorithm and you exploit it. So there's two components of a good cipher. The first one is permutation, where you transform letters to different letters. And the second, and another issue, is the mode of operation, which is how you're going to handle messages of arbitrary size. Now in the Caesar cipher, you encrypt one letter at a time, so there's no issue with the size of the message. It can be as long or as short as you want. But as we're going to see in most algorithms, there's a block size, and there's an issue of how you handle blocks, stuff that doesn't fit into a certain number of blocks of text. Now this is permutation, to transform one letter to another. The permutation should be determined by the key. Different keys should result in different permutations, and the permuted text should look random. There should be no patterns left in the ciphertext that the attacker can exploit to try to deduce the key or the plain text. The mode of operation will encrypt one letter at a time. That means double letters in the input will turn into double letters in the output, which is bad, because double letters are not randomly spaced in the English language, and just knowing where the double letters are it gives you a big step forward into deducing what the plain text is, and so on. This is an insecure method. It's now called electronic codebook mode, where you have blocks of data and you just encrypt them independently, so an identical input block will lead to an identical output block. Anyway, let's get to the perfect encryption scheme that's been known for centuries. This one is essentially perfect. First, you have to be able to combine two messages. One way is with XOR. XOR is just a way to combine bits, which is, of course, a useful thing these days. Now that we're not really trying to encrypt letters anymore, we're trying to encrypt bits and bytes because everything's a computer file. So, if the plain text is here, that's a 0 or 1, and the key is here, it's also a 0 or 1, all you do is an exclusive OR. So if the two are different, the answer is 1. If the two are the same, the answer is 0. So 0 XOR 0 is 0, and 1 XOR 1 is 0, but 0 XOR 1 and 1 XOR 0 is 1. This is a very desirable operation, and it lies at the heart of many modern encryption schemes, because XOR does not destroy information. When I first saw this, I wondered why you don't just use OR. If you used OR, 1 or 1 would be 1. And the result of that would be, if I feed in a plain text message that half zeros and half ones, the output would now be 3/4 ones and only 1/4 zero, and that would destroy information. So you would not be able to decrypt data. You have to have something that does not change the information content of the message. So if you feed it half zeros and half ones, the output still is half zeros and half ones. That's important. Otherwise, you are destroying information in the process and you're not going to be able to decrypt it. So now you can encrypt a stream of bits. Your key is just a random string of zeros and ones. Your plain text is a pattern of bits that encode something like ABC and ASCII, and now you get the ciphertext. If the key is random and never reused, then the key, you have to first distribute a big block of key to the person you're sending your data to, so they have enough keys for all the messages you will ever send. And once you have distributed that key, this is perfectly unbreakable. Nobody's ever found any way to break it. If you imagine breaking this without the key, you'd make all possible patterns of bits here, and as a result, you would get all possible messages down here, including many readable messages that are wrong. One of them would be right, and you would have no way to know which one of them is right. So it seems absolutely perfect as long as you obey this rule. The key is random, so there is no pattern. There's no way to deduce something from the whatever key you're able to steal somewhere and figure out what key is coming after it, and you have to never reuse any part of the key. Each key is used only once. If you obey that rule, this is essentially perfect, and nobody has ever in centuries found any way to break into it, other than, of course, to physically steal the key. That's not a mathematical attack, but that's certainly a practical attack. Like, for example, if you just put a camera and a microphone in the room where people are encoding or decoding the message, you can just copy the message before it's encoded or decoded. There's always some way to steal anything, but you're not going to get it by reversing the one-time pad cipher. So let's try a Kahoot. These Kahoots are worth extra credit, and they also help stop people from falling asleep so much during the lecture. If you're in the top 3, you will get 3 points. So it's a small amount of extra credit, but it does add up throughout the semester. So if you want to play, open a browser and go to kahoot.it and type in that number and any name you like, although something resembling your real name is easiest for us to deal with. If you put in a fake name, we won't know who to give the points to unless you tell us who you really are. I'll be right back. All right, let's give it a try. All right, so which one of these must be kept secret? All right, in modern systems, what's recommended is you have to keep the key secret and you do not need to keep the algorithm secret. Although the military likes to keep them both secret, but most people recommend these days you should just use a standard algorithm that everybody knows, that everybody has tested, and the only thing you keep secret is the key. Which of these is the weakest? Caesar is ridiculously weak. Children often break it with no computer just for Sunday comics fun. You really only have to try a maximum of 26 guesses to get in, and all you have to do is read through it and find some short words you can guess, and you can pretty much do it in your head. It's amazingly weak. Which is the most difficult to use? The one-time pad is difficult to use because you have to distribute some huge block of one-time pad to the other person somehow. All right. And which process allows messages of various sizes to be encrypted? Called the mode of operation, and we're going to talk a lot more about it as we go ahead. It is a way for an otherwise secure system to still have a serious security flaw by choosing an unwise mode. All right, I'm not sure if my grader will succeed in figuring out who you are from those names. You can try it, or you can give me more information, whichever suits you. All right, so to talk about security of an encryption scheme. So in order to decide how secure a cryptographic scheme is, you don't just give it a number in a vacuum, you have to have an attack model. This is true of all aspects of security. If you want something secure, you have to define this more carefully. Nothing is ever perfectly secure, and so you have to consider secure against what sort of attack. So that's the game here. Decide what attack you're worried about, and then decide whether your system can withstand that attack, and then you can decide whether it's secure for your purposes. Here's an XKCD about it. If someone uses 4096-bit RSA, you're never getting in by guessing the key, but you could always, like I say, find another way. Drug him and hit him with a wrench until he gives us the password, or sneak a bug in to record the message before it gets encrypted, something like that. There's always a way in. All cryptography can do is block the mathematical way in. So Kirchhoff's principles, the one I mentioned, here's the rule. The key is secret, but the cipher is not secret. This is the way most people recommend doing it these days. In general, if some company gives you an encrypted thing and they will not tell you what encryption scheme they're using, it is best to not buy or use that product, because invariably they're doing something stupid. If they won't tell you, almost always they're shown to have invented their own method, and if you think you're smart enough to invent a cryptographic method, you are wrong. The methods we use have been invented by the smartest mathematicians in the world. Unless you are well beyond a PhD in mathematics, you have no business inventing a cryptographic method. All you're doing is fooling yourself by thinking, oh, I could shift every letter one to the left and then XOR it together. If they have an idea in the shower, and it's going to turn out to mathematically reduce to something that was invented centuries ago and broken centuries ago. Very smart people have considered this, and if you think you have a secret proprietary encryption method, nobody should trust you. You'd be much better off to just get them to use a standard algorithm like RSA or AES, where we know how it works. All right, anyway, so if you want to test your model, one way is a black box model, where you just attack it without knowing anything about what happens inside the encryption. All you see is the ciphertext. Or you can have a known plain text attack, where you know the plain text and the ciphertext, and you can try to deduce the key. There's a chosen plain text attack where I can feed in plain text and you will encrypt it. For example, a wireless network. I can just send wireless packets on the network and it will encrypt it and send them off, and I can look at the encrypted stuff. And then chosen ciphertext is where you can actually perform encryption and decryption. And depending on which of these, certain models can withstand these attacks, other models can't. Then there's gray box models where you can actually tamper with the system's internals. Now, in a side channel attack, you can measure something about the operation without modifying it, like the timing or the power consumption. And that's non-invasive attack where you don't modify anything, but you actually have access not just to the output of the encryption, but you have access to the hardware doing the encryption, so you can measure some other property of the hardware, like the power consumption. And then there's invasive attacks where you actually modify the system. And this is fault injection is the main way this is done. This is extremely powerful. This is how Joe Grand broke into a cryptocurrency wallet to get the lost password. You inject a voltage spike in the power supply, causing it to crash and freeze partway through its calculation, and you can frequently cause it to freeze at a moment when something important is in the memory, like the key. And there are other tricks too. So you can also dissolve part of a microchip. That's another one Joe Grand did. Windows computers are protected by a trusted platform module, which is a cryptographic coprocessor that holds the key for BitLocker drive encryption. And Joe Grand, a famous hacker, dissolved the trusted platform model with acid until he was able to reach in with a microscopic probe and find the wire containing the key and pump it out. So that's another way to attack the hardware to find the secret, as opposed to some kind of mathematical deduction. All right, so here's some possible security goals. One thing is ciphertext should just look like a random string, shouldn't have any patterns at all. Another one is non-malleability. You will not be able to alter the ciphertext and create something which will also decrypt to meaningful plaintext. This, by the way, is something that is not true of the Caesar cipher. In the Caesar cipher, I could take some words of the Caesar cipher and rearrange them and send them, and they would decrypt to possibly a meaningful sentence. So they don't have either of these properties. The Caesar cipher doesn't. Here's some more notions. Indistinguishability against a chosen plaintext attack. So two identical plaintext strings have to result in different ciphertexts, which I mentioned. This is something that electronic codebook mode fails to do. A block of input leads to a fixed block of output based on the key, and if you have another identical block of input, you get the same block of output. Better algorithms add some random stuff every time, so that even if you have two blocks of identical input, you will get different outputs. All right, and then of course there's asymmetric encryption. This is the newest. The previous system I've described is symmetric encryption with this key. That's been known for thousands of years, and it's the only kind of encryption the human race had until 1979, except for the NSA, which had asymmetric encryption a couple of decades earlier, reportedly, but it was classified, but it was independently invented by Whitfield and Diffie, mathematicians outside the NSA, in 1979. So in 1979, they developed this system where you have two keys called public key encryption. Everybody has a public key and a private key, and now you can send secrets without having to previously exchange a hidden key. So it is wonderful. It's a huge step forward in cryptography, and we'll cover it in great detail in later chapters, but we're not going to do any of that in this chapter. So, ciphers can do more than encryption, and this is part of what leads to security problems as people abuse ciphers for things they weren't designed for. For example, authenticated encryption. On authenticated encryption, you feed in plain text and a key, and you get two things out. You get ciphertext and an authentication tag. The ciphertext, of course, provides confidentiality. Nobody can get in there without the key. And the authentication tag proves that you know who sent this message. It's like a signature. And both of these are supposed to be unforgeable and easy to verify. And that's the idea. That's authenticated encryption. So now you know the message has not been altered. That's integrity. And you also know the identity of the author. Then there's format preserving encryption. Now, this is something you might need. Suppose you have an online social network or something like Facebook, and you have fields that are full of unencrypted data like credit card numbers and social security numbers and so on, and then you decide later we really should encrypt that stuff. But we don't want to reformat our whole database and all our help page, everything tied on it, so we want to format it, but we want it to still maintain the same structure. So normally encryption takes things into random bits, but you could make an encryption that turns a zip code into something that still looks like a zip code, or an IP address into something that still looks like an IP address, and they call that format preserving encryption. Then there is homomorphic encryption, which is like black magic. This is really brand new, and some very early betas of it are available. We have a couple of projects where you get to play with it, but I haven't really seen any of this get fast enough to be practically useful yet, although I have had some vendors claim over the last couple of years that they've got it running fast enough. This is where you actually do mathematical operations on data without decrypting it. It's very new. The first fully homomorphic encryption scheme was created in 2009, but the result is, if you think about this, suppose, for example, something that you may not remember, but over the last several years it was important, you might need to prove that you have taken a COVID vaccine to enter a bar or get a job or something. And if you think about the current system, if you belong to a health plan like Kaiser, people at Kaiser have the ability to log into your account and they can see your whole medical history. Now, to get into like a bar, you probably don't want that person to know your whole medical history, but it'd be nice to verify that you shot the vaccine. And with homomorphic encryption, you could structure a query that would go up to a database and ask one question, like, did this person take the vaccine? And it would get the answer to that question without exposing all that other information. So it's really important for privacy. There's a lot of desire for this, and homomorphic encryption, people are working for it. Is format preserving encryption different than tokenization? Yes, I think it is. Tokenization is just reducing something down to a token. Format preserving encryption, I suppose you could regard it as a special case of tokenization if you want to. I guess I'm not exactly sure what the precise definition of tokenization is, but yeah, you could look at it that way. All right, anyway, so that's what they call searchable encryption. You can search encrypted data and without decrypting it. And then you would only get a certain amount of information out of it. And as people get more and more interested in privacy, this, I think, will have more and more demand for this stuff, but it's in its very early stages yet, homomorphic encryption. Then there's tweakable encryption. This is unfortunately very common due to a requirement written in the hard disk encryption standard, where you'd have to have a tweak parameter. And the problem is, when I first heard of encrypting hard drives, I thought, well, this is pretty easy. You just take a key, you encrypt the hard drive with something like AES, then you hide the key somewhere like in the Trusted Platform module, and Bob's your uncle. But the problem is, the official standard saying what hard drive encryption should be said a hard drive might be shared by many users, and each user must have the ability to encrypt just their portion of the hard drive so no other user can see it. So it's not enough to just have one key that opens the whole hard drive. You'd have to have a whole bunch of keys. So in addition to the key, you'd have to have this tweak parameter, which identifies who the user is and makes it possible for each user to show what part of the hard drive they're allowed to read. So anyway, this does happen in hard drives. And it does therefore make it pretty difficult for hard drives to actually meet the recommended standard of encryption. All right, you think at some point in the future we can use AI to crack encryption? Well, I haven't heard any proposals that suggest that that would be an improvement. As far as I know, encryption is not a problem that will benefit from machine learning, not yet. There may be some situation under which that happens. But I was just teaching the machine learning class on Saturday. We were talking about the problems that machine learning is good for, and I do not think cracking encryption is a likely candidate, although things might come up. But not I don't think so, not right away. Of course, in the future, something new may happen. But as far as breaking the existing schemes, it's a matter of trying millions and billions of keys, and you just want a really fast algorithm to do one boring thing over and over, and that's just what AI is not needed for. That's what classical algorithms are good for. So offhand, I don't see any benefit from AI, but people may develop something new. So, for example, the 2G phone network used this thing called the A51 cipher, and that turned out to be vulnerable to a time-memory trade-off attack. sooted Windows XP password hashes, where you could use a large block of memory to store a lookup table, and then you could do the attack very fast. Then you could try keys faster, and you could eventually try all the keys. Another one is the padding oracle attack. We'll do quite a bit later in the course. It turns out that if you give the user an error message, which is unnecessary, then they can use that to deduce information about the key. And this turned out to afflict a huge number of real software products, where they were using what was considered the most modern, safest kind of encryption, but they made a small implementation error, and that was enough to leak out data to deduce the key and find the ciphertext. So we'll do that in hands-on projects later. All right, and that's why people get afraid of encryption. The math can be good, but when you actually implement it in real hardware and real software, it's easy to make a little mistake which can shatter it like glass. All right, so let's take a look at another Kahoot. It's 1B here. Trying to improve my amateur theater setup here. It's pretty good. Have to get enough light on my green screen so it doesn't flicker. Anyway. All right. All right. So what's required to know whether a cipher is safe? You have to do attack modeling. This is something amateurs really don't like. They say, make it secure. Turn on security so it says yes. And you can't really do that. You have to model what you're worried about and then try to stop that attack. It's very unsatisfactory to amateur users. All right. All right. So the ciphertext only attack and known plaintext attack, what are they? Those are black box model attacks where you don't know anything about the internal operation of the algorithm. All you know is the inputs and outputs, and you try and attack it just on that basis. That's why they call it a black box. Everything inside is hidden in the darkness from you. All right, how about lowering the power supply voltage to cause errors? What kind of attack is that? That's an invasive attack, and I mentioned it's quite powerful. messing with the power supply, fault injection, and just lowering the power supply to cause errors. These are very powerful attacks. There was a paper came out about 15 years ago where they cracked 512-bit RSA with just 100 errors by lowering the voltage. If you can get 100 erroneous encryptions, then you can deduce the key from them if you know the algorithm. And they were attacking an open source RSA algorithm. All right, how about side channel attacks? What are they? Those are in the gray box model, where you have some ability to snoop on what's happening inside, although you don't alter it. This turns out to be very difficult to build any real hardware that will do encryption without leaking out data through radio or power or another way. Timing, very hard to withstand these side channel attacks. All right, CO. And that looks like socks. I don't know what those are. Hurricanes, maybe. Tornadoes. And Alex Cooper, there's the person that wants his points. The others may not want their points because I don't know who they are. All right. So, let me stop this recording.